In this module, we will introduce the concept of omega regular expressions. We have been seeing languages over finite words. We considered a finite alphabet. By a finite alphabet, we mean a finite set of symbols. Sigma star denotes the set of all words formed using this alphabet, and a language is just a set of finite words. Here are some examples of languages of finite words. A B, A B, A B, A B, A B, A B. This is a language. Words starting with an A, words starting with a B, and so on. We have seen this before. To describe languages of finite words, we used what are called regular expressions. For example, this is AB followed by any number of ABs. So this is AB, AB star. Word starting with an A is given by A sigma star. Words starting with a B are given by the regular expression B sigma star. The set of all words consisting only of B and the word epsilon, this set is given by B star. This is AB star. This is BBB star, and this one is word starting and ending with an A, so you have A sigma star A. This is a language for which we can't give a regular expression. Let me just recall the definition of star. So you took some sigma, and sigma dot sigma will be the set of all words of length 2. Sigma cube would be the words of length 3, and sigma per k would be words of length k. And if you take a union of all of them, we get sigma star. So this is going to be the set of all finite length words. The number of such words could be infinite, but each word in this set has a finite length. Let me be more precise about the definition of regular expressions. Epsilon is a regular expression, and the language of epsilon is just the singleton set consisting of the empty word. A and B, if sigma is A and B, then A and B are also regular expressions, and when I write A, it denotes the language consisting of the word A. When we write B, it denotes the language consisting of the word B. Now, how do we form more complex regular expressions? These are all the basic ones. Given two regular expressions R1 and R2, R1, R2 is a regular expression. Similarly, R1 plus R2 is also a regular expression. So the language of R1, R2 would be the words in R1 concatenated with words in R2. Similar to sigma dot sigma, here instead of sigma you have a language which is R1 and R2, and when you concatenate you get the set of all words which are formed by taking a word in R1 followed by taking a word in R2. R1 plus R2 is just the union. Take the language of R1, take the language of R2, and take the language consisting of words in R1 as well as R2, just the union. And finally, the star. So R par 0 would be epsilon, R par 1 would be the words in R dot R would be the words in R concatenated twice, in the sense you take a word in R, take some other word in R, or even the same word, and then concatenate them, similar to the sigma dot sigma. And then R cubed would be language of R dot language of R dot language of R. R star would be the union of each of these R par i's. Yeah, so here R1, R2 are regular expressions themselves. Here are some examples. Why is this a regular expression? A is a regular expression, and if you have a regular expression, the star of it is also a regular expression, so A star is a regular expression. Similarly, B is a regular expression. From B you can form B star, so A star and B star are regular expressions. Now we know that if R1 and R2 are regular expressions, then R1 plus R2 is a regular expression, so A star plus B star is a regular expression. Similarly, A is regular expression, B is a regular expression, so the concatenation R1, R2, AB is a regular expression. Similarly, BB is a regular expression, so you can add these two, R1 plus R2. This will be one regular expression. This will be yet another regular expression, so once again you can form the plus of these two, and so on. Here is a very important theorem. Given a regular expression, you can construct an NFA which accepts the language of the expression. For example, if you have A star plus B star, we know how to construct an NFA which accepts A star plus B star. Similarly, AB plus BB the whole star. We can convert this regular expression into an equivalent NFA. The theorem says that every regular expression can be converted to an NFA accepting the language of that expression. Similarly, every NFA can be converted to a regular expression describing the language of the NFA. This we have not seen examples, but you just take it for granted. You can refer a standard textbook on theory of computation or automata theory. You will find the proof of this theorem. In terms of describing languages, both regular expressions and NFAs are the same. You can describe a language of finite words either using a regular expression or using an NFA. There is no language for which you can come up only with an NFA and not a regular expression, and vice versa. Because of this theorem, we were calling languages accepted by NFAs as regular languages. This is something important. I hope you can see an illustration of this theorem on these small examples. So far, we have been seeing languages over finite words. We will now make a transition to languages over infinite words. Once again, we have an alphabet. The alphabet is finite, A and B. That's what we have taken here. Let me look at the infinite word consisting only of A. So this is the word. You can look at it as a function from the natural numbers to A comma B. So at 1 you have A, at 2 you have A, at 3 you have A, and so on. At every position you have an A. This is an infinite word. There is no length. This is not bounded by some length. This is not bounded by say 100 or 200, nothing. For every natural number, which is the position, there is an A. And the language is just the singleton, the single word consisting of infinitely many A's. This is one language of infinite words. Let us look at another example. To this infinite word, we also add the one where there is only B. Infinite words containing only A or only B. So this is one word, this is the second word where every position has a B. Again, both of them are infinite words. Another example of a language is a word in AA sigma star AA. This is a regular expression, so this will give us a language of finite words. You take some word in that language and then follow it up with only B's. Here are some examples. Look at A. So A belongs to this regular expression. I mean the language of this regular expression. So sigma is just A plus B. So the sigma star will also include epsilon, and AA would give us the word AAAA followed by only B's. Another example would be AA, BAB, AA. So this is a word in this regular expression followed by only B's. Similarly, AA, BB, AA. So this is the prefix followed only by B's. And so on. There are many words. So each of them is an infinite word, and there are infinitely many such words. This is one language over infinite words. Another example. Suppose I look at all infinite words where B occurs only finitely often. That means, for example, here in this word, B doesn't occur at all. So finite could include 0. Here B occurs only once, and after that there is no B. Here B occurs up to this position. After this position there is no B. So these are words where there is some position, and before that position there could be B's, but after that position there are only A's. So this is a language where B occurs only finitely often. Another language over infinite words. Words where B occurs infinitely often. So for example here AB, so on. So for every position you will have a future position where B is present. Okay? Look at this word BBBA, BBBA, BBBA and so on. Here there are only B's. Note that if B is occurring infinitely often, it doesn't mean that A occurs only finitely often. For example, look at this. Here both B and A can occur infinitely often. That's possible. This is just telling that get me all the words where B occurs infinitely often. So these are some languages over infinite words. A language of infinite words is just a set of infinite words. Similar as before, just that we will be considering infinite words. How do we describe such languages? For languages of finite words, we had regular expressions. Now for languages over infinite words, what do we have? I will give some idea of omega regular expressions in this slide. Look at this. We will denote this as a power omega. This is just a notation. This word is denoted as a power omega. This omega represents an operator denoting infinite repetition. Things will become clearer now. What about this? This is a power omega, this is b power omega, and this is going to be the union of these two. So a power omega plus b power omega. You should note that these are all notations for these languages. What about this? So something in AA sigma star AA followed by only B's. Here it is. AA sigma star AA concatenated with the word B power omega. So AA sigma star AA is a succinct notation for the set of all words which start with two A's and end with two A's. So there are infinitely many words here, and this is a word which contains only B's, and by using this dot you have the language described by this big English sentence. Sometimes we will just remove this dot. For example, here it is ideally A dot A, but for clarity we will not write the dot. What about this? It says that B occurs only finitely often. So after a position, you should see A power omega. Till that point, you can see any word. It can contain A, B, it may not contain B's, but you can see any word, and after that you should see only A's. And that is what is described by this expression. You see A plus B star, this is sigma star, you see some word followed by only B's. This is a more interesting thing. It says that B should occur infinitely often. There is no condition on A. A might occur infinitely often or not. So here we go. You see some number of A's, could be even 0. That is why we denote it as A star. Then you see a B, and this thing should be repeated infinitely often. For example, this one would be like AB, and then in the next thing you take AB, AB again. See, A star B is some language. By writing A star B per omega, you are taking some word each time from A star B. And you are doing this infinitely often. So here, you just take B, and in the next iteration again take B, again you take B, and then you take AB, then you take B, then you take B, and then you take AB, simply B, then AB, simply B, AB, and so on. A formal meaning for what this is would follow. These are called omega regular expressions. The general form is this. You take simple regular expressions that we saw before with the star, plus, and dot, and you can form an omega regular expression like this. E1 dot F1 per omega. For example, here E1 is this dot F1 per omega. F1 would be just B. And then once you have some number of such regular expressions, you can do a union. Okay, so an omega regular expression is written in this form. One thing to note is that none of these FIs should have the word epsilon as part of that language, because doing an infinite repetition of epsilon doesn't make sense. So we will assume that the expressions under the omega operation should not contain epsilon. For example, here we had B, it did not contain epsilon. Yet again here we had A star B. So A star might contain epsilon, but A star B, this expression does not contain epsilon. Okay. Here is a more precise meaning of F bar omega. So when we write F bar omega, the language represented by F bar omega is the set of all infinite words formed by taking words in this F. So F represents a regular expression. So it contains a set of finite words. You take some word in F, concatenate it with some word in F again, concatenate it with some word in F, and so on. So this is the set of all words of the form W1, W2, W3, such that each Wi is in the language of the regular expression. So here B per omega was simple, and we saw A star B. So A star B consists of all words B, AB, AAAB, AAAAB, and so on. And how do you form the language of A star B per omega? You take some word in A star B, concatenate it with some other word in A star B or the same word, again concatenate it with some word in A star B, and so on. Let us see some more examples. A plus B whole per omega would be the set of all infinite words. So A plus B star was the set of all finite words. Here A plus B per omega would be the set of all infinite words. So how do you form the language of this? You take something in A or B, then you take something in A or B, then you take something in A or B for the next position. For the next position again you take something from A or B, and so on. So you will get all possible words. Now this will be A plus B per omega would be all the words that start with an A. What about this? So this is A plus BC plus C per omega. So in this language, you will have words where whenever there is a B, the next position would be a C. So this is the set of all infinite words where every B is immediately followed by a C. What about this? So this is some word in A plus B star, and then you see this letter C, and then you see something in A plus B per omega. So this is a set of all words, all infinite words using just A and B. This is a set of all finite words using A and B, and there is a single C. So this will give us all possible words over the alphabet ABC where C occurs only once. What about this? This is similar to the previous case where we did B occurs infinitely often. Here, instead of just A star, we say that you can see some word involving A and B, some finite word, then you should see a C. Again, you can see some word, some finite word in A and B, and you should see a C. And again, some finite word using just A's and B's, and then you should see a C, and so on. So this is what this omega regular expression explains. At this point, we have seen many examples of omega regular expressions. We have also seen a definition of the omega operator. If you are clear with these examples and the definition, we can now see what omega regular properties are. Our goal is to specify properties using omega regular expressions. When we talk about properties, our sigma would be the power set of AP. So this is going to be the alphabet, and a property is a language of infinite words over this alphabet. And the property is said to be omega regular if it can be described by an omega regular expression. The property that you have in mind, if you can write an omega regular expression for it, for that language, then you call that property to be an omega regular property. Let's see an example. Suppose AP had two atomic propositions, weight and critical. So weight is true in states where the system is waiting to get into the critical section, and critical is true whenever the system is in its critical section. Look at this as P1, P2. Instead of P1, P2, we are looking at it as weight and crit. Now the alphabet would be the empty set, the set consisting only of weight, the set consisting only of crit, and then both weight and critical. Let me now describe a property. I want to say that process enters the critical section infinitely often. That means what? The letters consisting of this and this should occur infinitely often. So these two are like the C here. So what would the regular expression be? Here we are. You see this letter and this letter for some finite time, and then you should see either this one or this letter, and this whole thing is put under the omega. So we have seen two examples like this before where we wanted B to occur infinitely often and C to occur infinitely often. Here we need these two to occur infinitely often, and so you can see this and this sum for some finite length, and then you should see one of these, and again you can see some finite length word in this, and then you should see this, and again you should see a finite length word in this, and then you can see this, and so on. Okay, so this is how you can specify properties which are just languages of infinite words. And if you are able to come up with an omega regular expression for the property, it means that the property is omega regular. So this brings us to the end of this module. We saw what are omega regular expressions and what are omega regular properties. We have seen one example of omega regular properties, and we have seen many examples of omega regular expressions. Now the goal is, given a transition system and an omega regular property, how do we model check? In the sense, how do we check if the set of traces of this transition system are contained inside the language given by this omega regular expression?